The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Welcome to Coffee with Cluffy. Hey, we're delighted to have John Siegenthaler, engineer extraordinaire, with us today. He's going to do this topic, and this is the first time ever topic. In fact, you're going to see slides never seen before. Siggy built this presentation just for this topic, so I think this is going to be another good one and popular. Maybe we'll end up doing an hydronics issue on it. So most of the information that applies to the topic today would come out of this issue we've done a number of years ago on mixing and hydronic systems. We talked a little bit about boiler protection with thermostatic valves and different options, but as you'll see as we get going here, this is complete new information, and it's great information. It's timely information, and I think everybody will enjoy this. So I think, Siggy.
Yep. Well, good afternoon, folks. From a very nice, crisp autumn day in upstate New York, we're going to get into protecting boilers against flue gas condensation. So here's an overall listing of what we're going to take a look at. We'll start off with kind of what's the chemistry involved with flue gases. We want to draw a distinction here on the second one between what I refer to as intermittent versus sustained flue gas condensation. Our protection schemes are really focused on sustained flue gas condensation or prevention of that. And we're going to look at some various piping arrangements that have been in the industry, in some cases for decades, and we're going to evaluate those. Do they provide consistent protection against sustained flue gas condensation, or don't they? And what are the underlying reasons why a given method either does or does not protect the boiler? We're going to introduce the idea of a thermal clutch, the ability to decouple the boiler from the balance of the system, the load. And it's an essential part of being able to consistently protect that boiler. And then we're going to look at several different hardware combinations, mixing valves and variable speed circulators that, when properly applied, will provide that protection. So let's start off with the basic idea that anytime you combust a hydrocarbon fuel, and that would include natural gas, propane, fuel oil, wood, or other types of biomass, wherever you've got those hydrogen and carbon atoms, one of the byproducts you're going to get is water. And for the case of methane or natural gas, a very basic chemical reaction shows methane plus oxygen basically gives us carbon dioxide and water. And the water vapor that's produced is substantial. Just to get a feel for that, each therm of natural gas, that's 100,000 BTUs of chemical energy. If all the water vapor produced during combustion could be condensed back to a liquid, it would generate a little bit over a gallon of water. So a typical residential ModCon boiler that is operating with sustained flue gas condensation and condensing the majority of that water vapor is going to produce several gallons of condensate on a typical cold winter day. Now, sometimes people get confused about where is water coming from when you're burning wood as a fuel. And this could be cordwood, it could be wood chips, it could be pellets. You can actually have zero moisture content wood, and the only way you can do that is to take the wood and literally bake it above 212 degrees until there's no further weight loss. So standard firewood that's been dried might have a moisture content in the range anywhere from maybe 11 to perhaps 20% moisture. So obviously some of that is showing up in the combustion stream, but even if the wood had zero moisture, just breaking of the hydrogen and carbon bonds is going to produce a certain degree of water. So there's no such thing as burning a hydrocarbon fuel and not producing any water as a byproduct. Now, the chemical equation I've got up here is really very simplified. There are other chemicals that go into the mix. For example, with fuel oil, there's sulfur in the fuel oil, and it's a lot lower than it used to be, but you're going to get sulfur dioxide compounds, nitrogen oxide, or what we call NOx, There's going to be, in some cases, particulate matter that is more typical when there's a biomass fuel being burned. And there could also be chlorides. And one of the things to be mindful of in a mechanical room is not to have chemicals such as bleaches or laundry detergents or even refrigerant in the same space as an atmospheric boiler. Those chemicals can get into the air of the boiler room, the mechanical room, and get drawn into the combustion chamber. And they can create some very aggressive acids. Hydrochloric acid, hydrofluoric acid could be created from refrigerant getting involved with the combustion reaction. And these compounds actually give that water vapor a fairly low pH. That pH can be in a range of 3 to 4. And just as a comparison, vinegar has a pH of about 2.6. So this condensate is not pure water. This is a fairly aggressive acidic compound. And you can see those photos over on the right. This one photo at the top, this is a galvanized vent connector pipe. That pipe has actually only been in service about 6 months. And you can see down at the bottom here that it already has holes eaten right through it from the acidic effects of the condensate. And over here, we've got a copper tube boiler. And I don't know the exact circumstances, but it sure appears that that was operating at temperatures that allowed flue gases and the other chemical compounds associated with those flue gases, aside from water, to condense. And you can see some pretty severe corrosion on the cast iron end sections and some scaling on that copper tube. So sustained flue gas condensation is going to damage any type of boiler made out of steel, cast iron, or copper fin tube. So we need to protect boilers against that kind of damage. And that leads up to a first poll question. Have you seen evidence of corrosion in boilers or venting systems due to flue gas condensation?
It looks like, oh yeah, yes, 93%, no, 7%, Siggy. So that's a big number.
Yeah, so it's very evident that this is real. This is not hypothetical. This happens, and we want to again take steps to prevent it. So let's go back. Let's talk about some industry terminology. Now, over here, we're looking at a photo of a cast iron sectional boiler, gas-fired. You can see the cast iron sections here with the burners down at the bottom. Very typical atmospheric cast iron boiler. And oftentimes we'll see or read where this type of boiler is described as being a quote-unquote non-condensing boiler. And as a comparison, we might see a typical wall-hung boiler, a modulating condensing boiler, and oftentimes it's referred to as a condensing boiler. But I want to bring up a quote that really kind of hit home with me several years ago as the radiant panel market was first starting to take off in North America. And it comes from a fellow named Don Pratt, who was a trainer with Mestec. And Don was presenting how to use cast iron boilers in the context of low temperature distribution systems, radiant panel systems. And he made the statement, all boilers can be condensing boilers. And of course, at that time in the industry, we really didn't have many examples of condensing, purposely built condensing boilers. And so, of course, a lot of eyes were rolling, like, what does he mean by that? Well, what he means is pretty simple. If the water temperature coming back to the boiler, for whatever it's connected to, if that water temperature causes the surfaces that face the combustion chamber and the flue gas passages in the boiler to be below the dew point of those exhaust gases, they are going to condense. And this is a graph, actually the source of data on this graph comes right out of ASHRAE. And it shows that dew point on a gas-fired boiler, a typical rule of thumb is about 130 degrees. Now that will vary a little bit with fuel-air ratios and so forth. And we got another slide that will look at that. But before we leave this, rather than label the boiler on the left, that cast iron, steel, or copper tube boiler, rather than label it non-condensing, I'm going to use the term conventional boiler. And by that, I mean a boiler that was designed and intended to operate without sustained flue gas condensation. But again, keep in mind that misapplied or lacking proper controls, that boiler can condense, and the results are going to be bad. You're going to cause corrosion not only within the boiler, but also within the flue gas passages and possibly even up in the chimney. Here's a couple graphs I put in. It just shows that the dew point temperature for natural gas and oil both vary. They basically vary with the fuel-air ratio, and this just plots them as a percentage of carbon dioxide in the exhaust stream. One thing you can see here is that the flue or the dew point temperatures of natural gas are higher than the dew point temperatures for fuel oil. The reason for that is the higher hydrogen content in natural gas versus fuel oil. The more hydrogen that's present in the fuel, the more potential you have, or the greater the amount of water vapor that's going to be produced as part of that reaction. Now, over on the right, there's a graph. This is actually comes out of Hydronic's number 10, dealing with biomass systems. And that shows a relationship between moisture content in wood as well as the air-fuel ratio. And you can, if we look at the bottom axis, the air-fuel ratio, as we go from left to right, we're basically adding more and more air per unit of fuel. And that is bringing the dew point temperatures down. And that's because as we add more air to the combustion reaction, we're essentially drying out or causing a lower relative humidity in the combustion process. But you can also see that for a given air-fuel ratio, let's say right about in the middle of that graph at about 1.5, that as you have higher and higher moisture content in the wood, obviously you have more water present in the combustion reaction and the dew point goes up. So in general, the drier the wood, the better. If you're working with a cordwood type of boiler, you should really not be using any wood over 20% moisture content. Pellets are typically around an 8% moisture content. So the drier the wood, not only do you get more heating value out of the combustion, but the dew point temperatures go down. So you may be wondering, why are we talking about flue gas condensation? Why weren't we talking about this maybe 30 years ago, 40 years ago? And the answer really is that most of the systems going back into, I'll say, pre-1980s, were most of the residential, like commercial systems, even the bigger systems, were working with relatively high temperatures well above the dew point of those boilers. We might have water coming back to the boiler at 150, 160 degrees Fahrenheit, well above that dew point, and we had low mass heat emitters, which meant that the distribution system would warm up quickly. We didn't necessarily have to have a dedicated means of protecting the boiler against sustained flue gas condensation, because we got through that initial phase, that intermittent flue gas condensation that every boiler is going to experience at startup. On a cold startup, you can't avoid it. It's really a matter of how quickly does that intermittent flue gas condensation go away. If the boiler can rise in temperature quickly, which again, high temperature boilers with low mass distribution systems, we can quickly get above that dew point condition, and from there out, we don't have to be concerned about sustained flue gas condensation. Okay. So what's the breakdown today? One of the questions that came in on the webinar was, why worry about flue gas condensation if we're working with stainless steel condensing capable boilers? And really the market is just about split at this point. This is a graph that shows condensing versus, and again, here you see the term non-condensing down here. I'll use the term conventional boilers, referring to cast iron, carbon steel, or copper tube boilers. We're just about at a 50-50 split. You can see the trend is definitely going towards more of the higher efficiency boilers, but there's still a lot of boilers out there being sold, as well as boilers that are installed, that could be in situations where they need protection against flue gas condensation. In the residential market, the stats are just about the same. Roughly about 47% of the boilers sold in 2017 were quote unquote non-condensing. So again, we've got a lot of boilers in existence, as well as boilers that are still going out the door that need to be protected if they're tied into especially low temperature distribution systems. So we're going to go to another poll question here. What percentage of the boilers you install are conventional boilers? And that again means not intended to operate with sustained flue gas condensation.
All right, so we've got more than 75% at 14%, 50 to 74%, 20%, 25 to 49% at 23%, and less than 25% at 43%. That's the big number.
So again, it kind of parallels that industry data. That substantial amount of boilers going in today are capable of operating. In fact, are intended to really encourage flue gas condensation, but the other half are not. Okay, so let's keep going. So I want to talk about a very general concept that needs to be understood to understand why certain things do protect the boiler, whereas other techniques do not protect the boiler. And one of those concepts is thermal equilibrium. So what I've got here on the screen is just a boiler. Let's say it's a conventional boiler. It's capable of putting out 50,000 BTUs per hour. And over on the right side, we've got a radiant distribution system. And if I recall properly, that is 6 circuits of 300-foot length, half-inch tubing in a slab. And so what I did is I modeled how warm does the water temperature have to be for that distribution system to dissipate 50,000 BTUs per hour. And the number that you come up with is 111.4 degrees. In other words, if I supply that radiant distribution system with 111.4 degree water, it can dissipate 50,000 BTUs per hour. And of course, that's as much heat as the boiler can put out running full tilt. So the bottom line is this: that water temperature will never rise above 111.4 degrees. If you set the aquastat on the boiler to a higher temperature, it's really irrelevant because the boiler is running full tilt and the distribution system is capable of dissipating its full output without the need of the water temperature on the supply side of the system going above 111.4. So this is that idea of thermal equilibrium. Every hydronic system will seek to operate at a set of conditions where there's a balance between the rate of heat input at the heat source and the rate of heat dissipation at the heat emitters or the distribution system as a whole. And it's only controls that can get in the way of that. But in this case, if we were to turn the high limit controller on that boiler up, we could turn it up to 200 degrees. It will not make a difference in that water temperature as long as that system operates as I've shown it there. In other words, as long as the circulator is on, the boiler's putting out 50,000, and there's no changes like zoning or anything going on in the distribution system, that system will stabilize at that 111.4 degrees. And you can see the return temperature calculates out to about 93, which is well below that nominal 130 degrees we talked about. So those little blue drops inside the boiler are bad news there. That's flue gas condensation. So what does it take to consistently prevent sustained flue gas condensation? And I'm emphasizing consistently, meaning under all operating conditions, not just steady state conditions, but startup and shutdown conditions, conditions where, for example, a high mass zone that's been off for hours might turn on and send, in a sense, a slug of cold water back towards the heat source. How do we create piping and controls that can consistently understand what's going on and protect the boiler? And it really comes down to two things. We have to measure and respond to the boiler inlet temperature. if we're not measuring that boiler inlet temperature, we cannot consistently guarantee that we're protecting against flue gas condensation. The second thing is we have to have a means of decoupling the boiler from the balance of the system. Now, that doesn't actually mean physically cutting a pipe or anything like that. It means that we have to have a way to prevent heat being generated by that boiler from being transferred to the balance of the system. And here's a schematic that shows kind of the concept here, okay? The system must have a means of limiting the rate of heat transfer between the boiler and the balance of the system. And you might be thinking, well, what does that mean? If that boiler could put out 100,000 BTUs per hour, how could the distribution system possibly take up more heat than 100,000 BTUs per hour? Well, think about a cold concrete slab on a startup condition. You can actually send water into a slab like that at, I'll pick a temperature, 105 degrees Fahrenheit. It could come back at 60 degrees or even less, depending on how cold that slab is. The delta T could be easily 3 times what the normal design load delta T is. You're going through a transient condition in that system, and under those conditions, the slab is actually pulling heat out of the water significantly faster than the boiler can produce that heat. So we get into this imbalance between heat production and heat dissipation. And as we said earlier, every system tries to adjust so we get a balance between those two rates of heat transfer. And the way it adjusts is the water temperature goes down. And all of a sudden that cast iron boiler, where the aquastat might be set for 180 degrees, has water coming back to it well below the dew point, and you could be in for hour after hour of sustained flue gas condensation. So the mixing assembly, this gray box here, I can show you several hardware options that go into that, but think of that as the clutch. Think of the boiler and the boiler loop as the engine in a vehicle. Think of the distribution system as your transmission and drivetrain. We need to have a clutch in between those. And I use the term thermal clutch, and that simply means a way to limit the rate of heat transfer from the boiler loop over into the distribution system when necessary. Okay. Says here, proper boiler protection does not allow the rate of heat extraction from the boiler to exceed the rate at which the boiler produces heat. Now, one of the questions that comes up quite often on the subject of boiler protection is, but if I'm limiting the rate of heat transfer from the boiler to the distribution system, doesn't that limit how fast the building can heat up? And the answer is no, because when that boiler is being protected, it should be running nonstop. It is producing heat as fast as it can. We can't make a 50,000 BTU per hour boiler into a 70,000 BTU per hour boiler. So when that boiler is running flat out, it's producing whatever heat it can. All the boiler protection scheme is doing is not allowing the distribution system to exceed the rate of heat production. Okay. Now, here's one of the, I'll call it traditional piping assemblies that you'll see if you go back and look at older literature in the field. You see the idea of a manual bypass valve in a system like this. And the thinking is that hot water from up here on the supply side of the system will partially bleed down through this valve and mix with cooler water coming back, and that will boost the boiler temperature coming back. And the answer is to that, yes, you will get some boost effect there. The real question, though, is does it provide enough boost effect and provide it consistently to prevent flue gas condensation? So we go back to our 2 criteria. First of all, there's no way to decouple the load from the heat source in this. There's no way. Short of shutting off the circulator, and of course that, obviously there's no heat transfer there. But we have no way to keep the boiler operating and sending, generating heat and decouple it from the balance of the system. And there's no sensing of boiler inlet temperature. So both of those conditions that we said were necessary for consistent protection against sustained flue gas condensation, neither of those conditions is there. So that is not going to work. And I call this a legacy detail. It's a detail that's been in the industry primarily to protect boilers against thermal shock. the idea of cold water coming back from the system, hitting a very hot cast iron section in a boiler, it could crack the section. But I want to stress that thermal shock and protection against sustained flue gas condensation are two different things. This does provide some bypass that would take the edge off of that really cold water coming back. So I can say, yeah, it does provide some degree of thermal shock protection, but it does not provide sustained or protection against sustained flue gas condensation. So how about if we change it over to a circulator? Okay, here's the idea of a bypass circulator. We can now generate perhaps more flow from up here at this upper T down through that circulator. You can get a better mixing effect down at the bottom. So again, go back to those two criteria. There's no way to smoothly decouple the load. Now, what do I mean by smoothly? A modulating process. We could argue that we could shut off this circulator, what I'll call the distribution circulator, leave this one running, and then when the boiler temperature comes back up, we could shut off the bypass and then turn this one back on. And I call that toggling of circulators. Now, that is used in the biomass industry to some extent. And the reason that it works is there's a lot of thermal mass in the system. There's relatively high water content in the boiler, and there's a lot of water content in the balance of system. So I'll liken this to having your foot on a clutch pedal in a truck, and you only have two ways you can set the clutch pedal. It's either all the way down to the floorboard or it's all the way out. You cannot modulate the clutch pedal. And obviously, if you've ever driven with a clutch, that's a pretty rough ride. So as far as an ability to smoothly transition heat from the boiler over to the load, we can't do that with this. And there's no sensing of boiler inlet temperature. So again, it's the black X, okay? Again, it was a legacy detail, very likely associated with trying to protect the boiler against thermal shock. Another question that comes up is, will primary secondary piping provide boiler protection? So here's a primary loop with 3 secondary loads attached to it. Ask the same questions. Is the boiler inlet temperature being measured? I don't see any sensor or any way to do that. And we don't really have any way to smoothly decouple the load. So again, both of our criteria are not being met. Primary secondary piping in and of itself does not protect the boiler against sustained flue gas condensation. Well, how about if we get rid of that primary loop and put in one of these new hydraulic separators? Same situation. Ask the questions. Do you see anything there that is measuring boiler inlet temperature? Or is there a way to smoothly decouple the boiler loop from the balance of the system? The answer is no. So again, just putting in a hydraulic separator by itself does not provide consistent protection against sustained flue gas condensation. Now, a little later on, I'm going to show you there's a simple modification for the schematic that leaves most of it in place, but does add a mixing valve which can provide that protection. Here's another one. How about a variable speed bypass circulator? This is going back to that earlier schematic. And instead of just turning that bypass circulator on and off, we're going to make it a variable speed circulator, and we're actually going to sense the boiler inlet temperature and allow that circulator to speed up as the boiler inlet temperature goes down. Okay, but again, ask the same questions. Now, the boiler temperature is being sensed and reacted to, so we're okay there. But again, there's no way to decouple that boiler from that thermal storage tank. And I'm using the thermal storage tank just as an example of a high thermal mass load. That could just as easily be a radiant floor slab. So again, this schematic by itself does not provide that protection. But fortunately, you can make a very simple change in the piping and it changes that scenario. We're using the same circulator with a temperature sensor measuring boiler inlet temperature, but now we've set up the boiler loop with a decoupling piping assembly, a pair of closely spaced T's. If this circulator slows down or stops, and this circulator is still running, that water just does a U-turn right here. So you can think of this in combination with the variable speed circulator as that thermal clutch. We're essentially allowing the load to communicate with the boiler loop to the degree where the rate of heat transfer doesn't exceed what the boiler's output is. But if the boiler cannot keep up with the load, we are sensing the boiler inlet temperature, and we will see that drop as evidence that the load is extracting heat faster than the boiler can produce it. And the reaction to that would be the variable speed pump slows down and perhaps even shuts off. The nice thing about this is that the variable speed pump does represent a modulating, smooth process for taking heat from the boiler loop into the load. Okay. So we do have boiler protection. It's just simply a matter of putting those closely spaced tees and having that ability to decouple the boiler from the load. Now, here's a three-way motorized mixing valve. This is actually a schematic right out of Hydronic's number 7, the reference issue. And the question again would be, would that three-way valve provide protection? Well, it's actually that same system we modeled earlier, except I've put the three-way mixing valve in there. And it says here that the mixing valve controller was set for 125 degrees. In other words, this mixing valve is trying to make 125 degree water right here at the sensor. And we're back to that 111.4 degrees. That system's in thermal equilibrium. The mixing valve is wide open, the bypass is fully closed, and it's as if the mixing valve isn't even there. And you can see the return temperature coming back into the boiler is 93 degrees. We're definitely experiencing flue gas condensation there. So again, boiler inlet temperature is not being sensed, and we're not providing protection. How about if we just put a pair of closely spaced tees in here? Okay. Well, we now have a way to decouple the load from the boiler loop because of the closely spaced tees. But again, look around. We don't see any device down here that's measuring the boiler inlet temperature and communicating to that mixing valve controller. So we do have decoupling from the load, but we do not have boiler inlet temperature being sensed. We don't have boiler protection. Now we have one more in the sequence. Same system piping, identical. All that has been added here is a boiler inlet temperature sensor that goes up to the controller that operates the motorized mixing valve. Most of the controllers that are on the market today that are intended to interface a conventional boiler to a low temperature system, anything operating a mixing controller, has a setting for the minimum boiler temperature. It can measure that boiler inlet temperature and when necessary, throttle down on the hot water port to prevent the distribution system from pulling in heat faster than the boiler can produce it. So by adding the boiler inlet temperature sensor and availing the control logic that's in the mixing valve controller, we've now got the boiler up above the, well, you can see we're holding the boiler inlet temperature in this case at 130. If we set the minimum boiler inlet temperature on the controller a little bit higher, the boiler loop would just go to a higher temperature. So we could set it, for example, for 135 if we wanted to, and we would be a little bit higher in temperature. So again, this meets both criteria. It measures the boiler inlet temperature and it has that decoupling. So we do have boiler protection. Here's another schematic that comes out of Hydronic 7. This shows you 6 different hardware arrangements that all provide for protection against sustained flue gas condensation. You can use a pair of 3-way thermostatic valves. One valve is monitoring boiler inlet temperature, the other is controlling supply temperature. We could use a 3-way motorized valve with a boiler return temperature sensor. We could do the same thing with a 4-way motorized mixing valve. This is a 2-way thermostatic valve with a capillary tube measuring supply, combined with a thermostatic 3-way valve to provide boiler protection. This one is a motorized 2-way valve. This is 2-way or injection mixing using a 2-way valve. But again, notice there is a sensor measuring that boiler inlet temperature. And then finally, we can use a variable speed injection pump. So there are plenty of hardware options out there that do provide both these criteria that we've talked about, that boiler inlet temperature sensing, as well as a decoupling means between the boiler loop and the system. One of the other products that's out there, this shows a high capacity 3-way thermostatic valve. And I'm showing this in the context of a cordwood gasification boiler, which was really its intended market is to provide boiler protection on these biomass boilers. But this valve could be used with any type of conventional boiler. You could protect a cast iron boiler, a steel boiler, copper tube boiler. What's different about this valve is that it has a high CV, meaning it has a high flow capacity. And if you look at that valve, you'll see there's no knob on there to adjust that temperature. That temperature can be changed by changing the thermostatic cartridge inside the valve. But the idea is that you would buy this valve with a specific temperature setting and install it, and there's really no need to touch it at that point. And it can't be, accidentally adjusted to a temperature lower than what would provide the flue gas condensation protection. So that's a product that can be used in any type of conventional boiler. And here's a schematic we looked at earlier where we've got a hydraulic separator in there. The separator is also providing our air and dirt separation, magnetic particle separation. All that I've done with that schematic is I've added that valve, that high flow capacity thermostatic valve. And now we do have our criteria where we do have the ability to separate the boiler loop. When necessary, that water is just basically doing this circuit right here. When that water is below the temperature setting of this valve, it's just recirculating back to the boiler. It's not getting out to the load. And of course, we are measuring and reacting to that temperature. As that temperature comes up, then this valve starts to open up the cold water inlet and reduce the flow of the bypass. And eventually, if we get well above the dew point, the bypass would be fully closed and it would just be a pass through from the what I'll call the quote unquote cool port to the boiler inlet port. Okay, so here's another hardware option. Again, this was aimed at the biomass market. So pellet boilers, cordwood gasification boilers. Essentially what this does is puts the circulator and the mixing valve together into one assembly. It's a little faster as far as installation, but it provides the same control functionality as if you were to install just the thermostatic valve as well as the circulator. So let's get our final poll question here. Do you currently install a means of boiler protection when using conventional boilers with low temperature distribution systems?
Yes, 70% of the people are saying yes and 30% no.
Okay. It's that 30% I'm concerned about.
Yeah. Expensive mistakes sometimes.
Okay, so we'll go back. So here's another method. This is kind of an interesting method. This is using a variable speed circulator, what I call a shuttle circulator. Pair of closely spaced T's. So we've got a boiler loop with a circulator here. Again, I'm showing this with a pellet boiler. This could be a cast iron boiler, a steel boiler, copper tube boiler. The shuttle circulator, I'm just showing a temperature sensor connected to it. In fact, I've got a specific TACO circulator down that does have the temperature capability or the temperature control function built into it. And up at the top here, I'm showing a differential pressure bypass valve that's set for about 1 PSI. And the reason that valve is in there, actually there's multiple functions for that valve. One is that a variable speed pump has a minimum curve to it. And I've actually plotted out for that TACO VT2218. This is the actual published pump curves for that. And you can see that it does have a minimum speed. So once it turns on and runs at minimal speed, if there was a very low resistance piping path that it was pumping against, it could potentially move enough water from for example, let's say this tank is very cool, it's at room temperature. Even if this thing is pumping 2 gallons or 3 gallons a minute against just this low flow resistance circuit, forget about this valve for the time being, that could still cause that boiler inlet temperature to stay below the dew point. So we need to have something that compensates for the fact that that pump can't go below a certain speed. And what I did is I took a look at the pressure versus flow curve on this. This happens to be the Caleffi differential pressure bypass valve. That can actually be set down to about 1 psi. And that would be sufficient to stop the flow even when that pump is running at its minimum speed. And by the way, when the pump, that particular pump runs at its minimum speed, it's only drawing about 9 watts, which is a very, very small amount of power. It's not going to harm the pump in any way that it's running at 9 watts and not actually creating any flow. It's just, there's just not enough power going into the pump to overheat the pump or, you know, cause damage to it. But once that pump starts to speed up, you can see here, as soon as it starts to speed up a little bit, the curve would switch up here and we start to get flow through there. So the bypass valve provides that gate with some forward opening resistance to it, as I say, about 1 psi if the valve, the bypass valve is fully open. The other thing that it does is it serves like a check valve. It prevents reverse thermosiphoning from the tank. Now, imagine we have this tank warm and we don't have any valve here at all, no check valve or delta P valve. What'll happen is the warm water will come out here, it'll start to cool, it'll descend, this pump would be off, and it'll just recirculate. This is called reverse thermosiphoning, and this will dissipate a fair amount of heat from that tank just sitting there. So we want to prevent that. And of course, the delta P valve has a spring in it that would close the disc against the seat whenever the pressure against the valve in the forward direction is less than 1 psi. So it takes the place of a check valve. So it's a nice little detail, and I do want to show that that detail can be scaled up. We got a slide coming up here. Here's another one. As we're discussing this webinar content, Hot Rod brought up the idea, what about old systems where there's several cast iron radiators and some big old black iron pipe? There's a lot of thermal mass in those systems. And if you're, especially if the building has been improved so that the load has been substantially reduced, it's possible that that cast iron radiator system might operate at a low water temperature, low enough to cause sustained flue gas condensation in a cast iron boiler or a steel boiler or copper tube boiler. So we can set up a very standard detail here. This is an injection mixing detail where we have a boiler loop and we have a variable speed pump that basically shuttles heat from the boiler loop into the distribution loop. And if we want to kind of bring our old cast iron system up to modern day standards, we could use an ECM variable speed pump here, and we could put thermostatic valves or radiator valves on each one of our radiators. And I'm just showing valves here with a capillary tube and a wall mounted knob. It could be other types of radiator valves as well, but this gives us individual control on each one of these cast iron radiators. And you'll see that there is a sensor here connected to that circulator that measures boiler return temperature. So we do have proper boiler protection built into this, as well as variable speed pumping and room by room zoning control. And I put one other schematic. This is just a zoomed in detail of this area, but I've put an outdoor sensor and a supply temperature sensor on it. There are standard controls in the industry that can do this. Not only will this provide boiler protection, but it will provide outdoor reset control of the supply water temperature to the distribution system. So very much a state-of-the-art control upgrade for that old cast iron radiator system. And here's that schematic, or a very similar schematic where we're using a variable speed pump. You recall in the previous schematic, I was showing a small Taco VT2218 circulator, which would be adequate for a residential system. But what if we are, for example, doing a pellet boiler and it's a 400,000 B2 per hour boiler? that little circulator just isn't big enough to shuttle heat away from the boiler to the load when that boiler's at full output. So we could go to a larger circulator. I'm showing an example here. This happens to be an Armstrong ECM circulator, and there's a family of these pumps. Most of the pump manufacturers now do have commercial grade or commercial size ECM circulators, and most of them can accept some type of a speed control signal. They don't necessarily have the temperature logic built into them to provide boiler protection, but we can use an external controller. And I showed an example of a controller down here. These are used in building automation systems or industrial type of systems. A controller like that is about $100. It measures a temperature sensor and can put out a 0 to 10 volt signal or a 4 to 20 milliamp signal. And basically it is going to provide the brains to watch that boiler inlet temperature. And then as that temperature rises, it will start to speed up this circulator here, which is going to pull heat away from the hydraulic separator and send it off to the load. So this concept of a variable speed shuttle circulator for boiler protection is applicable all the way up the line. It's just a matter of getting a controller that can measure that boiler inlet temperature and then speed up that pump when necessary. And look,
Okay.
This came in from Jerry, and the question is, how well does a circulator hold off feature work from a cold start? And I believe what Jerry's referring to there is a control that would simply keep the circulator off in the boiler circulator off until the boiler gets up to a certain temperature and then turn it on.
Yep.
That could work. In fact, again, some of the pellet boilers from Europe use that type of means of boiler protection. It works, but it's not a modulating process. And by that, I mean, think about what's going to happen is the boiler is going to rise in temperature relatively quickly. If there's no flow going through it, it's going to get to some temperature. The circulator is going to turn on, and essentially it's going to pull a slug of cool water back in where there was hot water in the boiler. So that circulator will probably only run for, perhaps 30 seconds, something like that. Depends on the water and the mass content of the boiler. Then it's going to shut off again. So we're going to get this toggling where that pump goes on and off and on and off. I think it would work, assuming that the temperature setting is high enough. My suggestion, though, would be I would only use that on a boiler system that has relatively high thermal mass. Otherwise, you're just going to be turning that pump on and off like every few seconds. So thanks, Jerry, for that question.
I think some of the Viessmann cast iron boilers that I installed years and years ago had that option where they had a, just an aquastat in there. They had a nice little triple well that went into the boiler, and one of the well sensors was an aquastat that would just turn the pump off for boiler. I mean, I call it a bang bang control.
Yep.
Yes, it's better than nothing at all. Somewhere between the pump just running wild and a bypass, globe valve or something in there. At least they had a little bit of logic to it. But you're right, it'd be on off all the time. One other thing.
I think that boiler too, those older Viessmanns, I think they had a fairly high water content.
Yeah, it was a
high thermal mass content. So
it was a big boiler. The other comment I wanted to make on when you were showing the thermostatic mixing valve, the high CV valve that we make, others make a valve like that specifically for boiler protection. They're available with different temperature sensors in them, and you want to be careful with the one you select. Yeah, if you go back to that, there you go. I think the Cluffy one we offer it comes with a 130, and I believe you can get two other temperatures. I think you can get down to 115 and maybe a higher temperature. And what I got this exact thing going on in my system. I put that valve in there with the 130, and what happens? It's got an 18 degree what you call differential, I guess. So if you add the 18 degree, what was happening is my boiler has a variable speed inducer motor like you see on that one there, and my boiler was starting to ramp down its output before the valve got to that 18 degree plus the 130. So I was starting to lose my full output of the boiler. So I went down to a lower size, went to the 115 plus the 18 degree differential, got me pretty close to the protection I wanted. So that's why when you buy one of those, know that they will have a couple choices in the sensor that you can put in it to to kind of fine tune them to what your application is.
Yeah,
And on the next one, Siggy, on the next one, the with the pump in it has a little gravity gate in it too, because on this valve here, we had a person install this and said they tried to fill the boiler. They had a check valve, like you show in the drawing there, and they had their boiler fill over on the tank side of the drawing, and they couldn't get the boiler filled up because the
okay. That's actually
yeah.
Yeah.
And he's right. It won't go through that valve when it's cold. So he had to put a little bypass line over to the boiler to fill it from the right side of the draw.
Yep. So when that valve's at room temperature, this what I'll call the cool pore is completely closed.
Yeah, it closes tight enough that he couldn't get water across to fill the boiler, and he had a check valve up above, of course.
So he probably had his fill coming in here versus down here.
Exactly. He had it over on the distribution somewhere downstream there. So.
Okay.
But he was using one of our drawings. In fact, the next drawing, if you want to toggle to that, is the drawing he was using to do that, but he wasn't using this exact valve. And this valve does have the ability with that little, if you want to explain that, how that gravity gate or check valve in there.
Yep.
Yeah. There
yeah.
You go.
So that's going to allow the water to go through. This is actually designed to allow thermosiphoning between the boiler and the tank during a power outage. And
Yep.
with a conventional boiler, that's not a big deal. But with a cordwood gasification boiler, you could have 60 pounds of firewood burning at full rate. Power goes out, and of course the pump is going to stop. So this allows that gravity flow or thermosiphoning, and that's actually what that little gate is for. That little gate would be held shut by the differential pressure of the pump when the pump is operating.
Yeah, and so you can fill through that one too. So
yep.
That was the difference between the drawing he was using. Wasn't using the exact component we showed, but we should make note of that in the future, that, you know, if you have a check valve in the three-way valve, you might not be able to fill through it. So let's see what else I got for questions. I think that
Hey, Hot Rod, this is Mike back in Milwaukee.
Yeah.
There was another question that came in about if a condensing boiler is made with a stainless steel heat exchanger, why worry about condensation?
Yeah, well, you know, we could look at, again, two very different intended operating modes for boilers today. We've got what we've referred to as conventional boilers, and that term simply means that boiler was designed and intended to operate without sustained flue gas condensation. And then we have the more modern boilers, the so-called ModCon boilers, modulated condensing boilers, with either stainless steel or in some cases aluminum heat exchangers. Those boilers are designed to encourage flue gas condensation. So, you know, that one is literally the flip side of the other in terms of, yes, we want flue gas condensation in a condensing boiler so we get the benefit of higher efficiency, whereas the other side is we want to do everything possible to prevent that sustained flue gas condensation. So if you're using a stainless steel condensing boiler or an aluminum condensing boiler, you do not need, nor do you want to provide any of these means of boiler protection. It's counterproductive. We want those boilers to operate with the coolest water possible coming back into the boiler so that we extract as much energy from those flue gases as possible by condensing that water vapor.
And then, Siggy, one other comment, and I know this is out there, that some of the cast iron boiler manufacturers now state in their installation manual that they can accept return temperature down to 110 degrees, but I think you'll find there's a mixing device under the hood if you look close at some of those. I know I had a Wild GV once, and it had a Hoffman mixing valve built right into it, and then I think later versions they put a variable speed pump in there, and I think the Burnham Revolution did that. And I don't know if a cast iron boiler, I know one of the German brands claimed they could take lower return temperature, but you know, you still got to protect the flue pipe and everything else in there. Even if the boiler has some special sauce on the cast iron that can withstand that lower temperature, you're going to have your condensation going on in the flue pipe. And you know, when you drive up to a building, one of the things I always look at on the service call is the B vent coming through the roof, and if it's all rusty and discolored up there, you know, going in that boiler's been running cold, that it's rusting out, that you know, maybe the roof flashing, the vent cap, and some of the piping up there. So I'd use that with a grain of caution. If the boiler says it can, you know, a cast iron boiler says it can take a return temperature, just make sure that you know, that's true, that there's some protection device in there. Is that what you're saying?
Some of the European cast iron boilers, some of them are still designed the cast iron sections are designed so that the return water comes back and actually goes along, I'll say, the outer portion of the cast iron section. It's not at that point contacting the surfaces where combustion gases are present. So the water comes back and essentially it gets a pre-warming effect as it goes through the outer portion of these cast iron sections. And then at the end of those sections, it does a U-turn and it comes back along the combustion chamber side of the section. So what they're doing is they're basically taking the heat that's in the outer portion of the cast iron section and getting that return water temperature elevated so that when it actually comes back closest to where the combustion gases are, it's above the dew point of the exhaust gases.
I see.
And different manufacturers, Viessmann, Badaris, and some of the other manufacturers, they use different techniques, but that was the basic idea, is basically stealing some heat from the outer portion of the section, preheating the water before it actually goes along the combustion side of the section. And it's an interesting idea. There's actually some pellet boilers that are doing that now. They're doing that in combination with a variable speed boiler circulator, and that is their means of boiler protection. They are not using external mixing devices, and that's fine if the manufacturer has that system worked out. That's fine, but that's typically the exception rather than the rule. Most boilers, especially the biomass boilers, today they do need some type of external boiler protection, either a loading unit, a high flow capacity mixing valve, or sometimes it's a three-way motorized valve with boiler return temperature sensing.
Yeah, and I think one other comment, a good comment from Kevin again, he said we might want to look at putting, and then this was a great catch, putting some DNA on our poll questions, because if there's manufacturers on here saying they always provide, it went through our polls off a little bit, and that's a good point. We didn't identify who's answering the question, because some of the people that are selling this equipment obviously build it in or know that, but not always the installers. So make sure we talk to you. So I guess thanks, Siggy. That was a great presentation. The slides are available. That was another question. At the end, if you hang on after we end here, there'll be a little survey, just a couple questions survey, and you can check a box if you want these slides, and we'll just send you the PDF of this, and get a hold of us anyways if you don't get that survey or have a chance to do that, and we'd be glad to share this this information with, and maybe you'll see it in the Hydronics upcoming also. So to make a long story long, I think that's it.
Okay, thank you all.
Thanks, everybody.